Shoucheng was really good at everything he did, and one of the things he was clearly good at it was marriage, and he was a very lucky person. So our next speaker is Xiaoliang Ji. Xiaoliang is one of the organizers of this conference. That sentence actually belies the fact that he did the lion's share of the work. So be sure to thank him for this conference. Okay, Xiaoliang.
Thank you. Hi, is this on? Thanks. I'm not sure if my microphone is on. Can you hear me?
Yes.
Good. Yeah, thanks, Barbara, very much for being here with us and give a wonderful speech as you always do, and thanks all of you for coming from all over the world to celebrate Shoucheng's science and life together with us. It's I can try this again. Okay. Before starting my talk, I want to say just one or two sentences about myself. I'm one of, I think many of us here feels we are a crowd of very, very lucky used to be young people or young people. And because we were advisees of Shoucheng, and I feel like I'm the luckiest among all of us because since I started working with Shoucheng in 2004, I stayed at Stanford as a postdoc and then as a faculty member, so I got the opportunity to talk extensively with Shoucheng and learn from him on all aspects for 14 years until the end of his life. So I feel like I'm, of course, the really luckiest person. So I just want to show a few photos that we had over the years. But I will leave more of my personal remarks to later, and during the dinner time, I think we will all have more time to talk about our memories, and hope you all will also tell us your experience. So, no, I don't. I just need a pointer. No, it's just. No, it's okay. I just need the laser.
Okay.
Where's the laser? Okay. But the purpose of this talk is to give an overview of Shoucheng's scientific life, and this is based on these posters that you see here. They are an overview prepared by the organizers of the workshop, especially Biao and Shaoxing, and Steve and Eugene and me, and also Xiaoqi Sun, the last PhD student of Shoucheng. He made this together with us. So I think I will start by saying that for all of us, of course, it's very difficult to overcome the sadness and shock of Shoucheng's early departure. However, we are very fortunate that Shoucheng has left us such a rich legacy and so many memories. So he, in his life as a friend and as a world-leading physicist, a remarkable advisor, and a great thinker. So in this talk, I mean, of course, it won't be possible to cover many things in such a rich scientific life of Shoucheng, but I would like to take a glance at his scientific life. So because it's impossible to cover so many magnificent contributions of Shoucheng in science, I feel like instead of going over the facts that most you all know already, I will focus on the idea, the flow of ideas of Shoucheng that we see when we look at his works. We try to follow and understand the ideas, how the connections between them, and how that inspired us. So that will be the main purpose of this talk. And you can see our posters for a more systematic summary. So I would like to draw a timeline as a outline of the talk. So we start by Shoucheng's early experience until his PhD, and then I will go over the several different directions. Of course, it's very hard to summarize Shoucheng's works in a few different fields because his works are so interdisciplinary, connecting different fields. But roughly, we could summarize this as a fractional quantum Hall and the SO5 theory on the HTC, and then the work starting from 2001, the 4D quantum Hall effect. I would like to summarize that as new topological state of matter. And then then the last part of the talk will be about beyond the physics, and you will hear that he has so many interests on other things, especially in the recent years. So Shoucheng was born in Shanghai in 1963, and he entered Fudan University in 1978. We already heard last night in the dinners that he skipped high school, and it was a Cultural Revolution time. It was and he was so outstanding, and he could get into the best, one of the top universities, and when he was 15, skipping the high school. So 1 year after he entered Fudan, he was selected to an exchange program that goes to the Free University of Berlin, and that's where he finished his bachelor degree. And this 4 years in Germany, as we heard also yesterday, the 4 years experience of Shoucheng in Germany is clearly very important to him. And I would like to mention one very important moment that Shoucheng often mentions. So this is his visit to Göttingen, to a very important cemetery, the name I couldn't pronounce, in Göttingen. And there is a lot of important mathematicians and physicists and scientists buried there. And Shoucheng visited the tombstones of them, and this is one of them, Otto Hahn. And so he, after this trip, Shoucheng wrote that he would spend my energy on the pursuit of science, hoping that I too would leave behind a life's work that could be summed up in a simple equation. So I think this was an important moment that he often remembers and inspired him, and he certainly has done that in a beautiful way. So after that, after the bachelor degree, he went to start his PhD in the Stony Brook University, and his PhD topic was supergravity, and his advisor is Professor Peter van Nieuwenhuizen. We are very glad that he will join us tonight, although he's still on the way. So this is a photo of Shoucheng and Peter and Barbara, and I think this is on the graduation. And we have another photo of them. Sorry, we have another photo around the same year here. So now I will start discussing the scientific works of Shoucheng, starting from the fractional quantum Hall effect. So I mean, probably Peter will talk more about his works before he switches to condensed matter in supergravity that I have no knowledge of. So I will start from in the final year of Shoucheng's PhD, he started to work in condensed matter, and I was following the suggestion of Professor Xiaoliang, one of his important role model and later lifelong friends. And so this is a photo of Barbara and Shoucheng and Professor Xiaoliang and Shoucheng's father, Hongfan Zhang. So I think you can see Shoucheng is very happy in both photos in Stony Brook, and I think that's not only because he's doing exciting science. I think this is also the same year he got married with Barbara. So when he started in condensed matter physics, he began a collaboration with Steve Kiverson, our chair today. He was a faculty member at Stony Brook, who later became Shoucheng's colleague and lifelong friend. So this is a photo of Shoucheng together with Steve and Pam, Steve's wife, and Perk back. So Shoucheng's work in fractional quantum Hall effect started about the effective field theory. So I won't give a long overview about fractional quantum Hall effect, but you know it was a quantization of the Hall conductance that's observed in 82 and was explained by Bob Laughlin's famous wave function. And then there is the question that how you describe this phenomena, the effect, not only the ground states, but all the important excitations at low energy in a way that's independent from all the details and universal. And that's the purpose of this work of Shoucheng and Hans Hansen and Steve. And that's the effective field theory, the Chern-Simons-Ginzburg-Landau theory. So that's the Lagrangian, and that's how the Chern-Simons theory enters quantum Hall effect. And so I would like to, so this is the topological field theory that captured the key features of the quantum Hall effect, the fractional quantum Hall effect, the fractional charge and fractional statistics. And also based on this theory, Shoucheng and Steve and Dang Hai, they later proposed a global phase diagram of fractional quantum Hall. There's beautiful electromagnetic dualities there. So I would like to emphasize that not only this work itself is very groundbreaking work in this field, it also set the style of Shoucheng's later research. That it's always his unique talent is with connecting the fundamental physics concepts with the reality in condensed matter systems. And this work is the first example, and it sets the style for all the later examples. That it's a beautiful field theory, and the topological physics summarized in a very nice Lagrangian, and it's connected directly to the experimental physics. And so also the other importance of the work is, of course, for all of us, the quantum Hall effect is one of the foundations that we know now of all the later developments of topological states of matter. And so later, so the second topic that Shoucheng touched was about the SO5 theory of high TC superconductivity. So the high TC superconductivity in cuprates was discovered in 1986, and that's when the superconducting temperature reached the liquid nitrogen level, and of course that started a lot of enthusiasm in condensed matter, and until today, this is a very important topic, and a lot of questions remains open. So it's not just the high temperature superconductivity that's interesting, but also the material has a very rich phase diagram that has many other phases. It's not just about why TC is high. There's many other interesting things there. Especially there are two important phases that are shared by all these materials, which is the superconducting phase and the antiferromagnetism. So they I could say they compete with each other in some way, and understanding how that affects superconductivity, that's an important task. And that's what Shoucheng attacked in 1997 by a theory by an effective field theory that's called SO5 theory. So it's based on a beautiful and simple idea that the superconducting order parameter is a complex number which is the same as two real numbers, and then the antiferromagnetism order parameter is a vector with 3 components. 2 plus 3 is 5. So Shoucheng's theory proposed a 5-dimensional parameter with SO5 symmetry as a parent state that leads to the two states. So the two phases of superconductivity and the antiferromagnetism are like symmetry breaking starting from the SO5. So you can see clearly this is like another example where some simple ideas like symmetry and symmetry breaking comes into condensed matter. And I would like to, and another important aspect I would like to emphasize about SO5 theory is there are a deep connection. When Shoucheng and the collaborators studied the SO5 theory, there is a deep connection between the SO5 and Dirac spinors, which wasn't noticed much before. And that becomes very important later. So you see these equations tells me that SO5 theory, then if you want to describe electron dynamics in SO5 in a theory with an SO5 order parameter, then the electrons transform in the spinors of SO5, just like how the relation between the ordinary like superconducting quasiparticles and the order parameters. So now then Shoucheng and Eugene and Songjun Jiangping, they studied these problems, and they especially emphasized that Dirac spinor, the 4-component Dirac spinor, and this is Shoucheng's note in 1997, where he wrote down the fermion operators, the 4-component spinors. So and this is I'm going to over the talk I'm going to show more of his handwriting notes. So one of the really fortunate thing for us is Shoucheng is so organized with all his notes, and he organized all his handwriting notes every year into a folder, and we have this folder for every year, and this is so like when we want to see what he's thinking about in that year, you can really just go there and see, and after the computer age, then he also have the electronic files organized exactly in the same way, and so we are really fortunate. I'm going to show these kind of these notes later, and going back to this topic, the Dirac spinors, interestingly, it becomes a theme. I feel it's like a theme of the music. It's like this thing appears again and again in Shoucheng's significant contributions. Although the later works we are going to talk about seems to be in a totally different field, but we come back to the same beautiful math in different ways. Okay, so as a summary of the two early topics, I think these two topics set up Shoucheng's the fundamental principle behind Shoucheng's work. The first work, Shen-Simons-Ginzburg-Landau theory, is about topology, and the second work, SO5, is about symmetry and symmetry breaking. Of course, symmetry is a fundamental principle in modern physics, and topology is a newer principle that we learned later. Then the symmetry and topology really become the fundamental principles that Shoucheng connects to all the realities in condensed matter. And so now the next topic so every turn, and also I had vividly this impression when I was a student, like 2000, 1999, I was already in college, so I heard about Shoucheng's works from time to time over news and also during his talks when he visited us. Every turn he takes looks like a total surprise, like his SO5 theory is about superconductivity, and then his next topic is about 4D quantum Hall. It looks, and later now we look back, we see the deep connection between them. So in 2005, Shoucheng and Jiangping proposed the 4D quantum Hall effect, and you see this is Shoucheng's note in 2001 about this effect. So again, I won't be able to summarize the science, but in this short time. But the key mathematical concept is to generalize complex number to quaternions. The complex number is essential for Bob Laughlin's Laughlin wave function. So if you generalize that to quaternions, you see naturally it's 4D. And again, when you think about actually this is Duncan Haldane work. When you write the quantum Hall wave function, the fractional quantum Hall wave function on the sphere, then you use the two-component spinors. So now the generalization is the Dirac four-component spinors. So this work, actually, so it looks like a totally like abstract work because we don't have 4 dimensions, but actually it leads to a lot of important things that becomes essential to the later developments in topological states of matter that we know. So besides its own value, this 4D quantum Hall introduced, I think, two important concepts. One is time-reversal invariance, and the other is emergent helicity. So you see, so the important thing is that when you generalize the quantum Hall to 4D, it becomes a spin current rather than a charge current. So it naturally is time-reversal invariant. And that as a first example reminded us or tell us, which sounds like for all of us who work in this field, it sounds obvious now, like we should ask, okay, there's time-reversal breaking topological states, quantum Hall. Is there a time-reversal invariant one? So these are, but these are totally not obvious questions at that time. So I think this is the one important thing that the 4D quantum Hall tell us. There is such a possibility. And the other important thing is that the edge states has emergent helicity, which means the spin and momentum are locked. And I think that leads Shoucheng to think about spin orbit coupling, because that's exactly what physically it means. And that leads to the next work. That's in 2003, 2 years after the 4D quantum Hall. So Shuichi Murakami, we are very glad that he's here, and Naoto Nagaoka and Shoucheng, they proposed this intrinsic spin Hall effect in 3D semiconductors. So coming back from 4D to 3D, and but you clearly see the connection between these two works, because the important thing in this work is the spin current and the response of spin current determined by electric field. And this equation itself tells us it's time reversal invariant, and another thing this equation tells us is it requires spin orbit coupling for it to be realized. So this is really the two important ideas that started in the 4D quantum Hall works, but then Shoucheng always think about how to relate these to reality. So I think in this work, the Shoucheng and collaborators, they come back to the realistic three-dimensional semiconductors. It's not 5 minutes, right? 9:30. No, it's, yeah, I changed the schedule, so I have to monitor. Sorry, I did tell the first two speakers, but sorry. So I think I needed half an hour, so I told the speakers I postponed for 10 minutes. Sorry. Anyway, so yeah, so the spin Hall effect was realized, and then so the important thing of spin orbit coupling and non-abelian Berry space plays an essential role in this work, and that actually is also many of us where we start learning about topological physics. That's from beautiful paper of them. Okay, so now, so as a summary of what I have shown, this is starting from these two works, then through this 4D quantum Hall and intrinsic spin Hall. I mean, I draw them as like islands, not because they are not important, but because like at that time, it still wasn't clear what is the connection between all the different topics. But then now, through this progress, we entered the new continent of new topological states, including the superconductors and insulators and superconductors. So it's impossible to summarize so many so many significant progress, significant contributions of Shoucheng in this what I call the age of discovery. So I would like to just summarize them in this timeline. And then the different colors represent different kind of contributions, like proposing the initial models, the blue ones, and proposing some realistic models that can be realized incrementally, and collaborating with incrementalists and realize these proposals, and then propose some effective field theory and general view that connect different states. So I'm going to just briefly mention several important contributions. So this is a initial model of quantum spin-Hall effect that's in 2004. And you see that in Shoucheng's handwritten notes. That was in June 2004, and he started to think about this question of how to realize quantize the spin-Hall effect using inhomogeneous spin orbit coupling. And there is the parallel work of Ken and Millie, where they realize time-Rosen invariant version of Duncan-Haldan's model, so these are the two initial works of quantum spin-Hall. And then after the two initial works, then the next important significant step is that the quantum spin-Hall is realized in mercury telluride following Shoucheng and Andre and Taylor's proposal. So of course you are all very familiar with this story. So I will just quickly emphasize that there is several reasons this work is so important. Of course, the first it's first a realistic topological, the new topological material, but also it proposed a minimal model that works very well for not only this case but other topological states. And it also proposed a general mechanism that's the band inversion. So this is realized in Lawrence Montenkamp's group in 2007. So we will hear more from him, our first speaker. So this is really the discovery of mercury telluride really heralded the beginning of this new era that of tremendous theoretical and experimental developments. So and I would like to show a photo. That's when Shoucheng and Lawrence and Charlie are receiving the Buckley Prize. And you also see Brian and Stuart and other colleagues here. So the next thing I would like to mention is in 2008 that Shoucheng and collaborators in Xidai and Zhongfang's group, they predicted the 3D TI in the Bismuth selenide family. So this now becomes the hydrogen atom of TI. This is not the first TI material, the 3D TI material, but it becomes the best TI material until today. And it also, I call it hydrogen atom because it's like the minimal model, and this is described by a simple model that's very similar to the BHZ work in the quantum spin-Hall case. And it's realized very soon after the proposal. And the 3D TI is basically a material with these surface electrons that has this emergent helicity. And then, so also in 2008, this is the work that Taylor Hughes and I worked together with Shoucheng. Then we proposed a topological field theory. So that's very, of course, a natural question for Shoucheng because he worked on he proposed the topological field theory for quantum Hall. So it's natural to ask topological field theory for the new TIs. So the topological field theory, interestingly, is closely related to the interesting high-energy physics in axion electrodynamics that we learned from Frank. So Frank Wilczek. So the consequence of the theory is a topological magnetoelectric effect, but also it leads to a systematic view of different topological states. So as a byproduct of trying to get the topological field theory of 3D TI, we actually get a more systematic way to get field theories for other TIs in different, and we realize that it's a systematic picture, not just one or two examples, but actually TI exists in every dimension and symmetry. And and together with two other independent works, this started the systematic understanding of now we know there's so many different topological states. And then one thing I would like to mention was the quantum anomalous Hall effect, but I will quickly go over that. So so this was something that, so the beginning was what we had a work in 2005, where it was mainly talking about quantum spin Hall, but we also mentioned that there could be a quantum anomalous Hall. So of course, the first model of this quantum anomalous Hall was actually already proposed by Duncan in 1988. But here we proposed a different model, and then later, Shoucheng's group proposed the more realistic proposals. So we try to relate this phenomena to reality, and there was two proposals. And the second one about the magnetic dope bismuth selenide was realized in 2013 in Qikun Xue's group. So I would like to show this photo. I think this is a nice photo that Shoucheng is discussing with Qikun Xue, and because it looks really lively. Like Claudia showed another one last night. Shoucheng was laughing, and I think this is, yeah, I really like these discussion moments. And you see this is about the quantum anomalous Hall. And in recent years, Shoucheng also was very interested in the topological superconductor, and especially the realization of the chiral topological superconductor using quantum anomalous Hall. So I would like to mention that this as a new possibility that realize topological quantum computation. Okay, so this is a really quick summary. I'm sorry, I'm already late. But I think you see that really based on these two principles, symmetry and topology, we got the Shoucheng made really contributions in all the different aspects of topological states of matter, including like make the first minimal models and realistic predictions, and then collaborate with experimentalists to realize them, and also like describe the topological effects and universal theory. So really, it's because he worked on all these different aspects, and that he connected all the different communities, then topological states of matter becomes a unique field in which the theory has an extraordinary prediction power. We don't often see that in condensed matter. So I would like to show as an example to show you how this field has become so rich, and we now know the new continent of topological states of matter is so big and so colorful. So this is the work last year by Andre Bernwig and Claudia Felser and collaborators, and I highlighted the size, the length of the paper. You see, you don't often see paper with 1958 pages. That's what tells us how the field has flourished in an amazing way. Topological materials in the world. Yeah. So okay, so that concludes the discussion about Shoucheng's physics contributions. But and in recent years, Shoucheng has done a lot of explorations beyond physics. Of course, it's not only recent years. He often told his students that you should spend 80% of your time on your specific research project, but you should spend the other 20% on the broader directions. So, and he himself always believes the science should have no disciplinary borders, and especially in recent years, Shoucheng investigated in many directions beyond physics, including like AI and blockchain, and the distributed computing, the secure computation, bioinformatics, and many other things. So you see there's a talk Shoucheng gave at Google this year. You can see that on YouTube. But I would like to show this very precious notes that we see from him in the 2018. So we see how many different directions that he's exploring, in only 1 year, how many different things. And this is just a snapshot of many things in the folder. So like the first page is about this CRISPR, CRISPR, the technique of gene editing. And the second one is about vector clock and causality, so some topic about relativity. And the third one is about some way of doing molecular diagnosis, something about biology. And the fourth one is about DNA fingerprinting. And then this one is about DAG, directed acyclic graph. So that's something that's applied to generalization of blockchain. That's what he's studying, he's thinking about. And then this one come back to physics, it's about Maxwell's demon and how it's related, how you think about it in the information theory way. And the last one we have in this folder was 2018, November 8th. And that's about zero knowledge proofs. How do you convince colorblind people color exists? So these amazing topics changing over all different fields, and you can see that there's really no border in his thinking, no border lines. And I would like to show the two important words. So Shoucheng worked on like AI, and there's the algorithm that Fei mentioned yesterday that relates atomic periodic tables to learn periodic tables from AI. And Shoucheng explored in this blockchain technology, and he coined this famous motto that's called "In Math We Trust," because he believed that humanity is now reaching a new era where trust and consensus is built upon math. If you were here yesterday during the service, you heard his voice. He was saying math is the language of God. So in all these different new directions, Shoucheng is exploring. So I was thinking, what is a good way to summarize all of them? And Brian, Shoucheng's son, suggested a very nice way to summarize all these different directions, and that's the algorithm for the future. So in this workshop, we will have a session on the Saturday afternoon about the algorithm for the future. And you can also count Shafi Goldweiser's talk tomorrow as in this session. So these are the so many different directions beyond physics. So I would like to end by citing the second line of the poem that of William Blake. That's Heaven in a Wildflower. So despite his abrupt departure, Shoucheng's groundbreaking scientific works, his dream and vision for science and life and humanity, and his inspiration to all of us will forever be preserved as an eternal monument to him, and it will be always in our hearts. But I will always, there's a photo I would love to show always, which is in, I think, 2009, when we all go on a hike at Russian Ridge, somewhere near here, and then we were all together seeing the sunset. So that the lighting really makes this looks a very nice representation of how Shoucheng led us in his vision. And you can see many of the people in the picture are here now. Okay, so I would like to end by thanking the Barbara and Stephanie and Brian and Ruth for providing all these precious photos and notes of Shoucheng, and also for helping us with the posters and the talk. And also thank many of you for giving helpful suggestions. Thank you.